Hi, my name is Panadero. I am presenting the work simplifying the data for the optimal sizing and operation of PV and storage in a household by linear transformation. That is a work in collaboration with Sebastián Martín and Juan Pérez. Within the content, first we have the introduction, then the problem statement, the aim and contribution, the method, the results, and the conclusion. Small-scale renewable energy generation is undergoing a rapid increase nowadays, in particular household photovoltaic generation. A key issue in the deployment of household installations with PV and storage is to calculate their optimal size. This problem can be posed as an optimization model and be solved within seconds in a regular laptop. But a practical problem arises. The data to fit the model are difficult to get or to manage for the people interested in solving the problem. It would be quite useful if we could get a good approximation to the optimal solution just using a reduced number of data values slightly available and with a clear interpretation. If we want to optimally size and operate an installation with PV, battery, and grid connection, and we have consumption and generation data for 1 year with hourly discretization, approximately 9,000 data, the research question is, of all this data, which is the really relevant information for the sizing and operation of the installation? Therefore, the aim is to get a model that uses a reduced number of data and produces a good approximation to the optimal solution. Figure 1 shows the relationship among the main grid and the household appliances, PV, battery, and the remaining demand. In order to contrast the solution, we define two linear programming problems, and one is the model that uses profiles with a large number of values and that produces the optimal solution. It is in the time domain T, and M2 uses a reduced number of average values and provides an approximation to the optimal solution. It is in the domain Q, which will be explained later. The objective function seeks to minimize the amortization cost and the average operating cost value. It is subject to the constraints shown on the slide. In order to answer the research question, we propose to build the M2 model using the following approaches, and this is the contribution of this work. 1. A partition of the time domain T, that is, to create subsets that group several time periods. Here, we define TQ as a partition of the set T. The subsets TQ inherit the ordering of the periods T in T, and the set of all the TQ is also an ordered set. We explore the definition of domain Q taking into account the intervals in a time of use tariff, 3 to 5 values, and for each day, the intervals where available PV generations equals 0 and those where it is not equal to 0 for all T in the interval. 2. A measure that summarizes information from these subsets into a single value. In this case, we use the mean value. For instance, if a subset consists of 1,000 time periods, instead of having 1,000 values, we have a single value, the average of those values, which represents the subset. Items 3 and 4 will be explained on the following slides. Number 3. The linear transformation, whose expression can be seen on the slide, transforms the equations of the original problem into consistent equations, using the value of the mean of each subset, variables and parameters with index t in M1 are vectors in T. Each vector in T is transformed in a vector of average values in Q. This vector of average values is used in M2 with the same name as in M1, but adding a hat. Number 4. The physical region of transformed M1 includes the physical region of M1 and some additional points. Among these points are charging and discharging the battery at the same time, and the amount of PV generation that can be used for direct self-consumption. These points can be removed by adding the constraints shown on the slide, where parameter PQ is a measure of correlation between the demand and PV generation inside each TQ. We apply the linear transformation that defines the average values to the equations in the model M1 to get the corresponding transformed equations in the model M2. Table 1 shows that in order to construct the subsets TQ, the condition that both PEC and PBAT remain constant for all T within the partition TQ has been taken into account. Table 2 shows the parameters used in both models, and Table 3 shows the value of parameters in domain Q. To illustrate the proposed methodology, M1 and M2 are applied to a type example of small size, and the solutions from both models are compared. This type example consists of a grid-connected household with PV and storage. The time horizon is a day, and the domain T contains 24 values. Values for demand and available PV generation are depicted in figure 2. The focus of the discussion here is on the difference between the solutions from both models. The value of PQ can be estimated from the available data. Here it is fitted by using a sensitivity analysis on PQ, as we can see in figure 3. The value for phi, as indicated on table 3, was selected because it corresponds to a zero error in net cost, which is represented by the green line. Figure 3 shows that values of error for PV, battery, and connection capacity are never zero, and their minimum value is reached for different values of phi. That means it is necessary to add more information to M2. As we can see in figure 4a, M2 overestimates the value of PV and connection capacity and underestimates the value of battery. The value of cost for direct consumption from grid is lower in M2 than in M1. Higher PV and lower cost for direct consumption from grid in M2 indicates the amount of PV self-consumption is higher in M2 than in M1. Also, the value of incomes for PV generation sold to the grid IVG is lower in M2 than in M1. This is because PV generation is used for self-consumption instead of for injection to grid. Again, we think this difference could be corrected by adding more information to M2. The presented approach is still raw, and despite of that, the errors are usually lower than 20%. As conclusion, M2 provides the same solution as M1 when applied on the non-reduced data. For the reduced data, some relevant solutions in both models as the net cost are quite similar, but other solutions as the optimal capacities show a significant error. Further research is required to identify the relevant information to be included in M2. Thank you very much for your attention.